Okay, couple of announcements. You have a flyer going around, if you don't have one, about the Senior Design Project course that we're going to run next quarter. And this is kind of academics meets the real world. We're getting projects from Google, from Pixar, from EA, from Sandia Labs, from the campus, from lots of people. We're getting projects that teams of 3 to 4 people can work on. And it's a 2-quarter course, right? 2 units each quarter. You have to take both quarters. Right, so it's kind of like Micromouse in the ECE department, but we're going to deal with projects that come from industry. And so there's some cool things coming from industry that we're working on right now, but this is all part of this course. Log on to the website, read the website if you want. The projects are going to start coming out there, we hope probably tomorrow, 1 or 2 at a time. And you can kind of see what's going on. But this is a new course we're going to do this year, next year, at least. And or we think next year with the creative budget situation that we are in at the university today. Ken doesn't know what he's teaching next year yet. So this is normally I do by now, but in general I don't. So we'll find out. But anyway, tell your friends about this course if they're interested too, and we'll see. What we can do. The other thing is that next, let's see, today is Monday, so on Wednesday I will show you some videos. Okay? Tell your friends, bring some popcorn if you like. Right? Pardon? Today's Wednesday? Today, you're right. Today is Wednesday. On Friday, I will show you some videos. Bring your friends if you want, popcorn, whatever. These are old videos, right? Kind of the I like to show them because they kind of show you that the transition on how animation started to go. They're all from Pixar or the company that became Pixar. And you'll find out why that little lamp jumps out and squishes the eye on the Pixar logo at the end of their movies. Okay, you'll find out why that's so. But I'll show some videos. We won't be taping that lecture because companies don't like to have their videos put out for public access, right? They would rather have me buy them, or you buy them, right? So, but they're kind of fun videos to go through, and we'll show you. We'll go through them a couple times and show you where and why things happen the way they do, where things happen, where the Bezier curves are, right? Things like that as we go through the videos. So it's kind of worth doing. And they range from just fun videos to there's a college party. There's kind of one that's a little darker. So it's kind of ranges the gamut of all. So I'll show these and we'll have a video day. So bring popcorn if you like, or whatever, or your food, or tell your friends. I mean, it's open to anybody can come see it, and we will do that. So that'll be on Friday. We'll do that. And your project is due a week from Friday, right? Okay. Week from Wednesday? Right?
On the 18th.
On the 18th? Okay. So, get up there and measure some things. We found out by walking around today there are a few things that you probably don't have to worry too much about. You can worry about the holes in the backs of the chairs if you wish, the plastic chairs. Don't worry about the holes, okay? There's other things. The stairway, we were down looking at the stairway today, and the railings on the stairway, I hadn't noticed this when I was first down there, but the railings on the stairway are curved. It's very slightly curved. And you can do this if you want. I mean, you can do it, but I'll let you make it so that there's these little sections of the stairways going up, individual sections. You can make them all straight if you like. I mean, it would be something that's really not that noticeable to do. But you can, I mean, there are nice ways of doing this, but I don't, that's beyond it. Also, secondly, do it with one light source first, okay? Not with many light sources, do it with one light source. Just get it working and all. You can't get shadows working, okay? We don't do shadows in this area. I'll show you how to do shadows here coming up probably next week. I'll show you how to do shadows using a Z-buffer algorithm, how we do shadows. Okay, but shadows don't work. So if you want shadows with your chairs on the floor, right, what you have to do is you have to put a little fuzzy black rectangle maybe under the chair. okay, if you want this to happen. And we do it all the time in our field, okay? If you watch Tiger Woods golf, if you play Tiger Woods golf and you watch Tiger Woods walking up to the tee, he's got two little spheres under his feet for shadows, okay, or two little circles under his feet for shadows. Okay, we do this all the time. Because we can't do shadows well, we approximate them. Okay. The other thing I've been asked is, if you want to model something, quite frequently you model a big floor, and then you have these funny stripes on the floor. How do you model the stripes? Right? For instance, well, what you do is you create this nice big huge floor, maybe textured if you like, right? And then you create another little polygon, which is the stripe, and you put it slightly above the floor that you have, okay, like 1/100 of an inch, okay, above the floor that you have, so it will be displayed. Quite frequently, if you put it exactly the same value in the plane of the floor, right, the program will very nicely give you a kind of a patterned, sometimes show it, sometimes not, right, because it can't figure out which is in front. Right, so you put it just slightly in front, or lift it up just slightly. We do this all the time also in graphics, okay? Things may look like they're all planar. In reality, they're this nice little layered things, okay, that we do. Go ahead.
Is there some minimum amount that you can adjust that? Because I did 0.01 and I did 0.02, but then the stuff on the bottom is still showing.
Stuff on the bottom is still showing 0.01. It depends on what scale you're using. And it depends on where near and far are, too. Okay? It depends on how you put near and far around your scene. So you'll have to experiment with that a bit. Okay? But in general, with these things, I'm not looking for perfect. We can't do perfect. Okay? I'm not looking for perfect, but we can do, some really good work down there in modeling these things. And in general, it's not too hard. But I'm not seeing enough people measuring stuff down there, so get started. Right? Get started. I should have a longer line outside my office, right, on Friday, of people saying, "Why? How do I do this? How do I do this? How do I do this?" Okay? So everybody okay? All right. Today, I'm going to give you an introduction to ray tracing. Okay? Now, I came to computer graphics in the late 1970s, and there was a whole bunch of these algorithms, and you've seen them. And there was one algorithm that everybody knew about, and that was ray tracing. And nobody had the guts to publish it. And it was really simple why this was so. And that's because it can obviously take so bloody long to do. Okay? The idea of ray tracing is, you'll love this, right? There's no image space. There's no viewing transform. There's no four-dimensional divide by W's. There's none of this, okay? What you do is you take and put a camera, right? A camera point, a little screen out here. Let me get my drawing skills going here. With a little screen out here in three-dimensional space, okay? And out here you have some scene, like the lobby in Kemper Hall, okay? And what you do is you put this camera out here. Let me make the camera point out a little farther, and kind of a screen. And the screen is going to correspond to what you actually see, okay? Now the idea is, for every pixel on this screen, so let's assume you have a bunch of pixels on the screen. For every pixel on the screen, you run a ray through that pixel, a straight line out into your scene. Okay, you run a straight line out. Okay, now typically we have this camera point C here, and we have kind of a unit vector that we call R that goes along the ray. Okay, and these develop a line. Okay, going through this pixel and going out. And so for every single pixel on the screen, we're going to take this ray and we're going to run it out. Okay, into our scene. So, you can see we're going to run quite a few pixels out, quite a few rays out, okay? And we're going to see what happens in the scene. And out here in the scene, you have a whole bunch of objects. And so what you're going to do is you're going to test this ray. against all your objects out here in the scene, right? And see which ones it hits. Okay, you're going to see which polygons, whatsoever, what this ray hits. Okay, now, and then what we have to do, if we can see where it hits, and we can see all the points out here, right? It hits these objects, various objects out here, right? And we can collect these points. If we collect all these points, all we have to do then is save the closest one, right? The closest one to our eye point. So we want to measure this distance. Yeah. Whoops. We want to measure that distance, say D, for every one of these points, okay? And we're going to select the one that's the closest one. Then what we're going to do is we're going to color, right? Use our Phong model or whatever and color this point, that color, okay? It's the simplest possible algorithms that you could kind of think of, right? And everybody knew it exists. And actually, one guy tried to give a lecture on it once and was kind of just laughed out of the audience, okay? And the reason was the following. Suppose you have 1,000 by 1,000, which today, that was a lot for the 70s, but today that's not bad to get a window 1,000 by 1,000 on your screen, right? And you want to ray trace here. Well, right off the top you can see you've got 1,000,000 vectors, right, that you have to generate and trace out, right? So there's 1,000,000 rays that you have to do. And out here, suppose you have 1,000 objects out here, okay, which isn't very many, by the way, which isn't very many. But suppose you had 1,000 objects out here. Well, for each one of these rays, you have to test against these 1,000 objects to see which one you hit and which one's the closest. So it's not hard to see that 1,000 times 1,000 times 1,000 is 1,000,000,000 operations without even talking about what you're going to do. You've got to do 1,000,000,000 things without even talking about what you're going to do. And I challenge you to go home tonight and write for I equal 1 to 1,000,000,000, A equal A plus 1, right? And run it and see how long it takes to run, okay? To extrapolate this back into the 1970s, and it was like, oh my God, you can't even think about this algorithm, okay? So this is simply ray tracing, okay? But we do it now, and we do it a lot, okay? And there's a couple reasons, okay? So I'll get to the reasons in a second. Let me show you what people do. So suppose I have this ray here. Okay, here's a C, or let me call it P for a second, and R, and this traces out. And suppose I have a sphere out here, right, of radius R. And here's the center of the sphere. That's why I wanted to use C. Here's the center of the sphere, okay? Now, I can tell very quickly by, let's see, we can measure the distance from a line to a point, okay? We can measure this distance from a line to a point actually quite easily. It happens to be a dot product, okay? If you look at this angle, and if you know the distance between P and C, right, then this distance here is actually what? There's a cosine of the angle involved or something like that, okay, to get it. So you can measure this distance D, right? If D is less than R, right, you've hit the sphere. If D is greater than R, you don't have to do anything else. You missed it, right? Throw it away, go to the next object, okay? If D is less than R, then there's a couple extra other things to do. You've hit the sphere. You've actually hit it in two places. Okay, every ray hits a sphere when it hits it. It hits it in two places unless you graze and you get exactly tangent to the sphere. Then it could hit just one. But numerical errors kind of mean that doesn't ever happen. Right? So you hit it in two places. And you can kind of look and see, you know that this distance here to this point is R. That's D. Right? So if you can measure this distance here, right, which you can by looking at cosines and all, you can measure this distance. Well, this distance you can measure also just by Pythagoras theorem. Here, D prime maybe. Okay? And you know you've hit the sphere at a distance this distance minus d and d prime, and this distance plus d prime. You know you've hit the sphere. So it's actually pretty easy to do. The hardest operation here is a square root. Okay? And actually we ran a profiler on a ray tracer that we wrote once, trying to improve the speed on it. And we found out that we found out a couple things. Number one, it was spending all of its time in our vector class, right? Right. So we inlined the entire vector class, which actually sped it up by about a factor of 3, it turned out. We inlined the entire vector class, got all the subroutine calls out, right? But then we found out that this thing was spending all the rest of its time in a square root routine. It's making unit vectors, it's doing square roots for spheres, etc. And part of the reason I'm doing this here is that it's not hard to figure out how to hit a sphere, how rays hit a sphere, which is kind of why when you see ray tracing algorithms, you see lots of spheres in the scenes, okay? Because spheres are really easy to do. Turns out cylinders aren't as bad to do. Suppose you have a plane here. Suppose you have a polygon. Suppose you have a polygon. And here's my ray coming in. It hits the plane of the polygon somewhere, okay? And if I look at the plane of the polygon, I can figure out a normal vector to this polygon. Here's a point P on the polygon here, okay? And if this is a point, oops, I've got too many P's. Let me call this Q. Let me call this P. And this is R for the ray, okay? And if you see this hits the plane, this plane of the polygon somewhere. I've drawn it outside the triangle. That we know that this point here, right, minus Q gives us a little vector, and these two vectors are perpendicular. We know that, okay? So this point down here is equal to, this point is equal to P plus T times R for some T, right? It's equal to P plus T times the vector R to get down to here for some T. Okay, and if R is a unit vector, T happens to be the distance. Okay. So this point down here, minus Q, dotted with, that's this vector, dotted with N has to be 0. Makes sense? And I think you can see here, if I play with this a bit, I'm going to write this as T times R dotted with N, right, plus P minus Q dotted with N has to be 0. Is that okay? I think so. And I can say that T then has to be a minus P minus Q dotted with N all over R dotted with N. Okay, like that. And so the cool thing is I can calculate T really fast. It's the ratio of two dot products. So I can figure out where a point hits the plane of a polygon really fast. Okay? Let's see. The only thing you have to worry about is if R dot N happens to be 0 here, right? You ought to occasionally look at these things. Let's see, if R dot N is 0, that means that R is perpendicular to N, right? Means that R is perpendicular to N. And if R is perpendicular to N, then it's never going to hit the plane, right? Unless it lies in the plane in the first place. Right? Things are never going to hit the plane if R is perpendicular to N. It has to be not perpendicular to N for it actually to hit the plane. So the question then determines, I can figure out how it hits the plane. How do I determine if it lies inside this polygon? Okay, go ahead.
Take respective dot products going around the vertices with some point on the inside, and if they're all the same sign.
There's about 18 different ways, and that's one of them, right? One of the ones that we have is, you remember barycentric coordinates for triangles, right? Barycentric coordinates said that any point here is equal to alpha 1 P1 plus alpha 2 P2 plus alpha 3 P3, where alpha 1 plus alpha 2 plus alpha 3 is 1. Okay? And given all these points, we can solve for alphas, turns out. Okay, because these are three x, y's, and z's, each one here. Right, we have enough information to solve for alphas. Right? And if all the alphas are between 0 and 1, it's in. If any of the alphas are not between 0 and 1, it's out. Okay? That's one way. Another way is to do, like suggested, like a clipping test all the way around. Right? Put a planes perpendicular to these things, do a clipping test all the way around, and it has to be in on every one. If it's ever out, it's not. There's another one that says run a line out to infinity in some direction. Actually, this thing is, believe it or not, this is used. Run a line from this point out to infinity in some direction. If this line crosses the polygon, if it's a convex polygon, if it crosses the polygon twice, an even number of times, it's out. Crosses it an odd number of times, it's in. Okay? This one is actually used too. This one is really, I don't like this one. Okay? Because you tend to choose lines that are really nice, right? And they also happen to be, you know, you get in trouble if you choose it just coincidentally along the edge, right, or through a point. You know, you get in trouble with this one. But there are many ways to do it. Right? Finding the intersection with a plane is easy. Right? Finding the second part is a little harder. Whether it's inside or out is a little harder. But you can do spheres, you can do triangles, which means you can do anything in polygons. Right? You can do cylinders, actually pretty easy too, etc. Okay, so ray tracing wasn't hard to do. This thing to find out, this is what? 10 lines of code to find out if it hits a sphere or where it hits a sphere. Right? This is more than 10 lines of code, right? Maybe some people 100 lines of code to do this one. Okay? So actually ray tracing was a reasonable thing to propose, except you got to do a billion things, right? You have to do a billion things. And that was not good. And then in 1980, there's a fellow named Turner Whitted. And Turner was a graduate of North Carolina. He owned a numerical analysis type company. Okay, and he was doing simulations for the nuclear power industry in which you're running photons around, right, tracing photons through the air. And Turner published this paper. Turner has one of these nice jobs now that at least I'd like to have, right, which is called a fellow at Microsoft, where they say, hey, you know, why don't you come up here, join Microsoft in Seattle. Just tell us how much you'd like the number to be on your paycheck, right? And we'd just like to put our name on anything you want. Come in if you like. We don't care. You know, it's one of those jobs we'd all like to have. He has one of those, right? But he published this paper that was kind of crazy. And what it said was, okay, this takes too long. Honest, it really does. It takes too long. Oh, see, one other thing. In 1980, there were 3 open problems that nobody could solve in computer graphics, right? You guys are coming up against one of these right away, right? Nobody could solve the problem of shadows. How do you do shadows? No one could do it well. You know, there were lots of papers being written, and nothing, you know, nothing really satisfactorily came out of it. The second problem was reflection. Suppose you have a mirror in your scene. How do you do mirror-like reflections in these things? And we can't do that with the image space type algorithms. We can't do mirrors. All right. So how do you do reflection? And people had done some weird stuff, and it hasn't really worked out either. And the third one was, how do you do refraction through an object? And suppose you had water, which we know the refractive index is for, right, and everything else. But how do you do refraction through objects? No one could figure that out. And there were these 3 open problems that people for 5 years had been trying to solve, and no one could. Well, Turner wrote this paper on ray tracing, and it said the following. It had this picture on the front. It said, here's a surface, okay? So take any point on this surface, and there's a normal vector, okay? And so we have this ray. Let me point it at my right point here. We have this ray coming in from the camera or whatever. And it comes in and intersects the surface there, okay? Now, everything's fine, right? We can figure out from the normal vector and all, we can look at the light source, we can do Phong shading, we can look at a point light source and everything else. But what Turner said was, hey, okay, suppose you've got a light source out here, right? Light source out here, point light source. We can determine if something is in shadow. How do we do that? What we do is we trace a ray toward the light source from this point, not from the camera. We trace a ray from this point toward the light source. Okay? We do exactly the same thing as we did for this ray coming from the camera. We look at the entire scene. All right? And what happens? We look at the entire scene. We keep track of all the things we hit with this ray. Okay? And what happens is we select the closest one. And if that one happens to be closer than the light source, right, we've got something in the way. And so what we're going to do is we're going to drop those things that come directly from the light source. And what they do is they drop the specular and diffuse part of the Phong equation and only do the ambient part in that case. Okay? And in this one little tiny paragraph, he killed the open problem. Right? Absolutely done. Everybody could now do shadows. Right? Immediately. And it was a trivial thing. It says, hey, if we can trace it from the light source, we can trace it from any other point. Big deal. Okay? And so basically what he did with the light sources is when you've got this illumination equation, which kind of says ambient plus diffuse times n dot L, right? Oops, n dot L plus specular. Oops, there's a base color out here. Specular times n dot H to the nth power, right? Well, if you can't see the light source, can't see the light source, just take these out of the equation and do only the ambient times the base color, right? And you get automatic shadows that take place. Okay? Well, then he said, this looks pretty close, but then he said, okay, that's one. Now I can do reflections also. How do I do reflections? Right? Well, I know that the angle of incident here in the these are awfully close. Let me modify my picture just slightly. Let's put the light source over there. I know that reflective comes from this perfectly reflecting, right, area, angle of incidence equal angle of reflection. I know it comes here, so if this is a reflective material, right, what I'm going to do is I'm going to trace, hold it. Let me stop, back up a bit. These are called shadow rays, right, we trace out. If you noticed, he took this absolutely intractable problem and traced a billion things and said, oh yeah, by the way, we're going to trace lots more, okay? We're going to trace lots more rays, right? And for every light source, well, we have 8 light sources. Well, from every point, we got to trace 8 more rays, okay? So I'll multiply that by 8, okay? And kind of, weird, but okay. So now we have this thing with reflection, angle of incidence equal angle of reflection. We can do the same thing. We can trace a light source, a light ray out here, and see what it hits. Okay, tracing a ray is just specifying the point and the vector itself. Okay, a point and the vector. And so when you get this equation here, what he said is if it's reflecting, add on another constant called the reflective constant times the illumination that comes in from this ray. Okay? So I'm going to run out and see what this ray hits, and I'm going to have it hit some object out here. Bang. Okay, I can figure out the closest object it hits. And I calculate the color for this object, right? And I add that just to the color that I calculated for the original, which might, in this part and this part, might be 0 if it's in shadow. It doesn't matter. I just calculate, I add on, right, a certain amount. Now, I want this constant, say, to be less than 1, because I don't want to add on, there's no perfectly reflecting surface, right, but I want to add on a little bit. And this was cool, too, right? Bango, there goes the reflection. Nobody could do reflection. Here's reflection, okay? The only problem with this one is you stop to think about it. Well, to determine what the shading is out here, I have to run a vector off to the light source, right? See if it's in shadow. Okay? See what's coming? And you really see it? What happens if this is reflective? Okay? All of a sudden, it's called recursion almost, right? Here we go. We got to trace another ray off here. And so all of a sudden, not only am I tracing a whole bunch of shadow rays more, but my reflective ray generates, if I hit something, it generates more shadow rays, and perhaps even another reflection ray. Okay? But it's all the same, because tracing these rays, all I need is the point the ray starts and a vector to trace them. Okay? Well, if you have an index of refraction between these two surfaces, you can also do a refractive ray to the inside. All you need is this index of refraction, and you can calculate the refractive ray. It takes about a line of code or two. And you could trace a ray to the inside, and so you can have these surfaces that actually refract light. And he wrote this world-famous paper, which is now, I think, the most referenced paper ever in the computer graphics field, and one of the most in computer science total, which in the very first page of the paper killed the three open problems, completely solved the three open problems we had in the field in that day using ray tracing. However, the problem is, right, all he said was, take that problem where I do 1 billion rays, no, yeah, trace more, right? Do a lot more. But what happened overnight in the computer graphics industry is we were all looking at problems of how to do things in near real time using graphics, and all of a sudden we weren't. Everybody was doing ray tracing, right? Spheres were popping out all over the place, transparent spheres, cat's eye spheres, everything were coming out all over the place. And what happened was the amount of computer time basically overnight went up by a huge factor that people were using in order to make pictures. And his first picture had 2 spheres and a checkerboard, 2 spheres and 1 polygon, right, with a texture on the polygon. That was his first picture, and it took 5.5 hours to produce. Okay, on the best machine of the day, which was a VAX 780. Okay, we can now do that one about 30 times a second on the machines that we have today. Okay, but it's only 2 spheres and it's only 1 checkerboard. And usually when you can download kind of Whited's first picture and run it, run the code, compile the code, and run it on your machine, and you can see it. And you can kind of rotate around in real time now. And most of it's downloaded onto the GPU too, so it's done in parallel on the GPU. But the whole thing was, then the whole field switched for about 10 years to doing this algorithm and ignoring all the rest. And what happened was that this algorithm kind of solves all your problems. That if but again, you have to be willing to trace this many. Now, go ahead.
Well, what if you, instead of doing ray tracing for each of the pixels, do somewhere along the phone model, do a Z buffer type thing, and for each pixel that you draw, do the respective point on the surface, and just trace rays off of that?
Yeah, you can do that. There's all kinds of ways to speed this up. Okay? Normally what happens when you speed up ray tracing is that you put some kind of data structure out here. Right? You put some kind of data structure out here. And the most common one, the most easy one to think about is one that is basically an octree. Okay? You basically sort all of your things into an octree. That's an octree? That's an octree. Okay? You put all these things into an octree. Okay? Now here I've only split it up into 8 pieces, but you shuffle all your things into these 8 bins. Okay? And then you split it up again. So you split this one up into 8 more. You split this one up into 8 more. You keep splitting, right? And you sort into these bins. And then what happens is you can stop, right, when each bin contains less than 5 objects maybe, or something like that. Depends on what you want to do. So, and then what you do is you trace your ray through the bins, okay? And when you hit a bin, you only trace against those objects in the bin, okay? And in this way, if one of these bins is far away from your ray, you'll never trace anything against those objects, right? You'll save considerable amount of time. Now you're trading off something that is, you have to trace against the bins now, okay? And it turns out that's not too hard to do. It happens to be almost identical to the algorithm where we draw a straight line on the screen and figure out what pixels to draw for a straight line. It turns out to be almost identical to that algorithm, and it can be done very, very quickly. But we don't quite do an octree anymore. We do variations of an octree called a KD tree, which is very common. KD tree, actually, this plane is usually in an octree is right in the middle, right? It can be shifted to one side or another depending on how many objects you got at certain parts of the screen. Okay, it's called a KD tree, and we do this. So there are ways to speed these up, but every problem, what's happened to ray tracing is that every problem that we've done in ray tracing has, the solution is always trace more rays. Okay? And we can solve almost anything, because this is really, let me show you that it's different, but this is really geometric optics. The geometric optics people, not the wave optics people, but the geometric ones, think of rays bouncing around, all over, rays of light energy bouncing around all over the place, and a few of them coming back into your eye. Actually, a lot of them hit your eye. But what happens is we can't do this bouncing around stuff. That takes too long when only a very few of them actually hit your eye. What we do is ray tracing actually thinks about these things and does them backwards. Okay? Some people call this now backwards ray tracing. What you do is you trace things out away from your eye and you see what they hit and color things accordingly. If they hit a mirror, you do another ray. Right? You put rays back to the shadows. If it's translucent, you do another ray, etc. And you trace these things away from your eye. Unfortunately, everything doesn't work well. Let's see, how can I do this? Suppose I have a mirror sitting here in this table. Okay, and I have a mirror on this side of the table, and I shine a flashlight with a hooded flashlight on this mirror, right? Now, I don't think it's too hard to convince you there's going to be a bright spot on the table, right? Because the light bounces off the mirror and hits the table. Right? There's going to be a bright spot on the table. Now, what I'm going to do in ray tracing is I'm going to trace a ray down to the table here, okay? And then I'm going to trace a shadow ray up to the light source, right? Hooded light source, so it never hits it maybe. Trace the shadow ray up to the light source, and I'm going to say that this thing's in shadow. Bang, done. Because I don't know that there's a mirror over there, right? And I don't know the exact perfect angle that light is bouncing down. So when I trace things backwards, I'm going to miss things. Okay? I'm going to miss some highlights. They don't come up. And over the years, in the late 90s, mid-late 90s, people started fixing this problem by what they called forward ray tracing. What they would do is kind of do this light bouncing around all over the place. They'd trace some rays from the light, right, out on to see what happens and bounce off the mirror. And then they would mark the surfaces where these light rays touched, okay, and know that that wasn't in shadow, for example. If you've ever seen the waves on the bottom of a swimming pool, right, those are refracted from the sun, right, and you don't know when you're looking at them, tracing rays away from your eye, you don't know the exact angle to reflect the ray through the water, right, to get to the sun. So you have to trace from the sun to the water, mark the bottom of the swimming pool, right, etc. And all of a sudden you can see this gets really complicated. Okay? It gets really complicated. There's also the things that can be solved by ray tracing, which is all the refractive light that you have running around. If you notice here, if you look up in the corners, it's darker than in the rest of the room. Right? The reason is the light energy from the lights doesn't go there directly. It all ends up bouncing around, okay, before it gets there. Right? We can actually approximate that using ray tracing. If when we hit a surface, we don't just do the perfect reflecting vector, we scatter rays in all directions and have this kind of function on how we're going to combine the light coming back in to the surface if we scatter rays in all directions. Scattering rays in all directions means you're doing not just a billion, you're doing billions and billions and billions. Right? So ray tracing solves all these problems, but it does so at a tremendous cost. And so we typically use parallel processors a lot for doing ray tracing. GPUs are great for ray tracing because each ray can kind of be done differently. Right? So we can just throw as many threads as the GPU can handle at it and have it do ray tracing for us. But this is it's a cool algorithm. It's there. One guy made it usable because he said, oh, all the problems we're having, we can solve them all, right, by using this ray tracing thing. And I've seen a ray tracer actually written up in about 350, 400 lines of code. The entire thing. I mean, nothing is that difficult to do with these things. I mean, we have to make unit vectors, square root every now and then, right? We have to figure out what's the vector between that point and that one. That's not hard. We have to figure out the points on the screen. That's not hard. As long as we have simple objects out in our scene, these aren't, the worst thing here is a square root. The worst thing here is it's kind of like a matrix equation, right, to figure this out. So the math isn't hard at all to do these things. What you can get is you can get a really nice ray tracer, right, without much code. Now there's some really nice ray tracers out there that you can now download and experiment with, and one is called PavRay. PavRay, and go Google it, right? You can download it, compile it, and it'll run, and you can make some nice, cool, pretty pictures with it, okay? But ray tracing is something that we usually look at in a graduate course, okay? We usually look at it in a graduate course. And now, oh, there's one other thing I have to do, right, is show you that it's not all easy. Lots of times we have surfaces that look like this. These are quite frequently the types of surfaces we get, okay, in science and everything else. Now the obvious one here is that's a sphere, okay? If I put A, B, and C here, that's an ellipse, turns out, okay? You can get elliptic equations, you can get everything. These are quite frequently the equations that we want to deal with, and they're all in this type of a form, okay? Well, if I have an equation, ray P plus T times R, right? If I write this in its components, right, this is xp plus T times xr, yp plus T times yr, zp plus T times zr, okay? I write this in its components and say, okay, I have this surface out here, fxy equals 0, and this ray out here going into it. This point, which is the point I want, happens to be where, right? Substitute the equation of the ray in for x, y, z, and you got to get 0, right? So f of xp plus T times xr, yp plus T times yr, zp plus T, comma, T times zr equals 0, okay? And this is a cool equation. It's got only one variable, T. Okay, it's got only one variable. I took the 3 variables now. I've got it down to 1, okay? And functions of one variable equal 0, right? That's kind of finding the roots of them, okay? But all of a sudden, things start to get kind of complex, right? That if you have a function x that has something like this in it, x squared, y squared, z squared, plus other stuff, right? Suppose I have a function that looks like this, right? When I plug in all these guys in here, this thing looks like some constant times t to the 6th plus other stuff, right? Because I'm going to square the x thing, I'm going to square the y thing, I'm going to square the z thing, and I'm going to get a t to the 6th power out of here, okay? And so you get this equation, and then you have to find out where that equals 0, okay? And some of us who went through undergraduate math took this course called algebra. It was required. Okay, and in the third quarter of the algebra course, they gave you you studied some things by a 19-year-old Frenchman called Galois. And Galois sat down one night when he was 19 years old and wrote out some really cool stuff, and then he went out the next morning and got shot in a duel over a young lady. But his name is famous for what he wrote down the night before he went out, basically. Okay? And what he did was effectively write down something we now call Galois theory today, which is used to prove something that if you have any polynomial equal to 0, right, there's a closed form solution for that. And what do I mean closed form solution? We have a closed form solution for any polynomial that has squared terms, right? Because that's called the quadratic formula that everybody learns in high school. There's a closed form solution for everything less than or equal to 5. Okay, you can do it for 5, believe it or not. You can do it for 3 and 4. You can get closed form. Oops, everything less than 5, sorry. Everything less than 5. Anything 5 and above, no hope. Which means in order to solve this, you have to do numerical analysis, right? And you have to do numerical analysis. And now think of a billion things and you got to do numerical analysis on all of them, okay? And start thinking about how long that's going to take. And there's been only a few people that have been crazy enough to do these numerical routines on things, and we at UC Davis are some of those, okay? That we published some papers on doing some really interesting surfaces. But it's very hard to do. The strategy is that if you can calculate it for one ray, the next ray, just a little tiny bit over, right? You can use what you calculated for the next the ray slightly before. You can use the first that solution is the first approximation for the next one, and it converges actually pretty rapidly. The only problem is what happens on the silhouette edges when you walk off, you know, and all of a sudden you're not on the same surface anymore, and then it costs you a lot of time to fix it back up. But so ray tracing looks easy, but in reality it's not. And all of the things down here, Bezier curves and B-spline curves and everything fit into that category. Okay? They just don't work out. So that's what's wrong with ray tracing, is that typically what we have to do a Bezier or a B-spline surface, have to subdivide it into triangles. Right? And then we do the triangles themselves, or something like that. So ray tracing then becomes really, really much more difficult to use. So anyway, that's ray tracing. Let's see. Now, Friday coming up. Today's Wednesday. Thank you. Friday coming up, I will show you some videos. It'll be fun. And you know, tell your friends if they want to have an interesting 1 to 2 hour to come and look at these things. You don't see them much anymore, these videos. They're actually quite good. The stories behind them are quite good. So I'll see you then.